Hey listeners, this is Gabe from Infomodel. We've just launched a crack assessment tool. Let's go over it. You'd start by clicking here, and it would bring you to our tool. Let's say you ran an inspection on a pipe, an EMAT tool, and it detects a colony of cracks. At the very edges of these cracks, there's extremely high stress. Under the wrong pressures, these cracks expand and lead to ruptures. We model these cracks under this pipeline view as a semi-elliptical floss shape. There's many known approaches in industry to determine the wrong pressure, the pressure where the pipe fails. We're using an approach very similar to the one provided here. You'd start by downloading the template sheet. I've already done this and inputted data. You put your IDs, so your anomaly identifier, your pipe name, your odometers, so the specific location of that anomaly, your begin chainage, end chainage, either for the pipe or the anomaly, your specified minimum yield strength, specified minimum tensile strength, Sharpie V-notch energy, and Sharpie impact area. Now, be very careful with these. Here I'm assuming a full specimen, which means that the Sharpie impact area is 0.124 inches squared. But if, let's say, you're using a 2/3 specimen or 1/3 specimen, you'd have to change both of these accordingly. So be very careful when inputting the values here. Make sure you know what you're doing. You've got your modulus of elasticity, your wall thickness, your outside diameter, operating pressure, flaw length, and your flaw depth. So all this data, what's your failure pressure? You would upload this into the cloud software, and right away you can view the results. So you can export the results as a CSV if you wanted, you can apply filters, and if, let's say, you're just interested in a few columns, you can filter things out. So I'm going to hide most of them, keep the anomaly ID, I'm going to keep the operating pressure, the ductile failure pressure, brittle failure pressure, final failure pressure, and the conclusion. So for your first ID, you're operating at about 1,000 to 150 psi. Your ductile failure pressure would be this number here. Your brittle failure pressure would be that number. You're looking for the smaller failure pressure. And as you can see, you're operating below the failure pressure. So in theory, you're operating at a safe pressure. Now, to explain the difference between these two failure pressures, there's two different failure modes. One mode where you've got something called necking, or material deformation that occurs before the material actually snaps off. So that's the plastic method. So the ductile fracture. But then there's another situation where you've got deformation that instantly breaks the pipe, and that's your brittle failure mechanism. It's a very different science, and the outcomes can be very different as well. But the idea is that we model both. The ductile one, something similar to corrosion, but with a semi-elliptical flaw shape, and the brittle one using something pretty complicated with J intervals. All in all, we capture both cases, take the lowest of the two for our failure pressure, and let you know if you're operating at a safe pressure. Thanks for listening.